I'm Helena, and I'm going to talk about a project I've been doing around non-elective patient flow simulation. So brief intro to me and where I work. So I work at the Countess of Chester Hospital. It's a medium-sized general and acute trust in the Northwest. And I started my current role as a senior analyst and data scientist about a year ago. My programming experience prior to the HSMA, I was not completely new to programming. I'd used R and SQL quite a lot before, but I was relatively new to Python. So quickly want to mention why I wanted to do the HSMA and where it fits into the work of our team. So in our analytics team, we get asked kind of broadly two types of questions, ones which involve kind of counting or extracting, like those on the left, and ones which involve kind of explaining or predicting or exploring something like those on the right. We're already quite good at answering the ones on the left with our existing tools and techniques, but we're trying to kind of develop our data science capacity in order to better answer the questions on the right, which involves new tools and techniques, which is what I wanted to learn about by doing the HSMA. So it's just to point out that even though you absolutely can do everything in R and Python, this hopefully demonstrates how the HSMA can be useful, even if R and Python aren't the primary tools your team uses, and how they can really extend your capabilities. Okay, so the specific project, the problem this project addresses is non-elective patient flow, which I'm sure is an issue that everyone's aware of because it's frequently in the news. It's a national issue, and it's also a problem at our hospital. So this is where demand for admission outstrips capacity to admit patients, often because there are no available beds, which results in patients waiting a long time in ED and often being cared for in areas like corridors, which are not designed for patient care. And it kind of causes a lot of congestion and other issues. And there's also evidence to show that admission delays cause real harm to patients and can increase inpatient length of stay, and patients have poorer outcomes. So yeah, it's a real patient safety issue and operational issue. And the role of the analytics team in this is to provide informative metrics to be able to monitor flow issues, and also be able to provide evidence and tools to help stakeholders understand the impacts of interventions when they're kind of trying to solve this problem. So I'm going to talk through a diagram of the model I made. So I used the same framework as Heath has just explained using SymPy and Python. This is a diagram. So it's a very high-level, simplified model of patient flow with the idea that I can add additional complexity in later if I need to. The model is only for non-elective patients who need admission. They are normally admitted by ED, but they can also be admitted via assessment units like SDEC. And in the model, we can vary demand via each of these routes. More we're measuring in the model, most interested in is metrics related to waits for admission in ED, which is why it's highlighted here. So the resources in the model are beds. So a patient will be admitted to a bed as soon as there is a bed free. They stay in the bed for a length of time that's based on our actual length of stay distribution, and we can alter the number of beds in the model. Once their inpatient length of stay has elapsed, the simulated patients will leave the model. Additionally, in addition to taking that kind of standard route through the model, patients can also be discharged from ED, even though they would have been admitted if there had been space, and this kind of becomes more likely the longer that they wait. This is to reflect what happens in reality when flow is poor, and patients following this route represent unmet demand for admission. And interestingly, we'll talk about this later, but unmet demand for admission isn't something that's often kind of considered or monitored. So in terms of management strategies or interventions, there are broadly only three things you can do to kind of improve flow. So decreasing inpatient length of stay, which is often talked about in terms of reducing discharge delays, increasing the number of beds, either via kind of actually expanding the funded bed base or by kind of opening temporary escalation beds, or decreasing demand for admission, normally via collaboration with system partners, but this is kind of more difficult for the hospital to have a direct impact on. But at the moment, aside from knowing that these three things are likely to help, we're unable to provide kind of very good evidence to support particular management interventions. So having the model allows us to try out different scenarios to provide evidence for interventions. So here are some examples. If we start with a scenario where we have 29 12-hour breaches per day in ED, we can try out some possible solutions. So if we open 10 more beds, breaches in the model are reduced to 14. If we reduce inpatient length of stay by 8 hours, breaches are reduced to 8 breaches per day. And if we send a higher proportion of admissions by SDEC, breaches are reduced from the starting scenario to 21. So kind of just add a caveat here that these figures shouldn't be treated as solid predictions. Like, the model has lots of simplifying assumptions, but they can provide a starting point for structuring kind of your thinking and structuring your interventions around the issue. So there's a little video. So in order to facilitate the use of the model for ad hoc scenarios, like I just described, I used the HSMA suggested framework of making an app using Streamlit. So this is a recording of what the app looks like. So the different inputs to the model are controlled using the sliders on the left. So there are sliders for demand, for beds, for length of stay. And then when the model is run, it shows a big table of metrics, including the main metrics we use to monitor waiting times in ED. It also shows a histogram and different scenarios broken down by run. And then in a minute, we'll also have a look at the animation tab, which, so I was able to make an animation which can help explain how the model works and sort of validate that it's running as expected. And I had a lot of help from Sammy, and it uses her wonderful animation package, which I'm very grateful for. And there's also a comparison tab, so you can run several different scenarios and compare them side by side. So hopefully show that. And yeah, so you can run 2 scenarios there, so you can see 2 different scenarios, inputs and outputs, but you can obviously run lots of different scenarios. Moving on. So in addition to running kind of ad hoc scenarios like we've just shown, we can also run the model in a more systematic way to provide an evidence base for targets. So for example, if number of beds and demand for admission are fixed, kind of how low does length of stay have to be so that we have no 12-hour waits in ED, so we can eliminate those 12-hour waits. So so we can see on the left of this chart, inpatient length of stay is low and there are no 12-hour breaches. As inpatient length of stay is increased, we reach a point where 12-hour waits start to occur, and if we increase it further, we reach a point where everyone is waiting 12 hours for admission. So this chart kind of enables us to find the maximum inpatient length of stay where no 12-hour breaches are occurring. So this shows us that it needs to be reduced to at least below this level to eliminate 12-hour waits, and gives us some target metrics to monitor performance against. And we can also relate this back to target reductions in non-criteria to reside. So we can also use the output of the model to inform how we're monitoring demand for admission. So actual admissions are often used as a proxy for demand for admission in both internal and external reporting. And here we can see why that doesn't give us an accurate picture of demand. So along the x-axis, I've run the model with increasing levels of demand and measured the numbers of admissions. So we can see on the left of the chart where the model hospital has spare capacity, admissions do equal demand, so it's a fair proxy. However, when demand starts to exceed capacity and flow problems start to occur, the 2 metrics diverge. So there's unmet demand. The number of people we're actually admitting is lower than the number of people we would admit if there was space. And this demonstrates it's very important to measure demand independently of admissions. So this has kind of prompted us to do that. So as well as displaying admissions and discharges, which are things kind of we already looked at and metrics we already showed on our dashboards, we've added estimated demand as a metric. And in practical terms, this demand figure is where our discharges need to be in order for us to meet that demand. So if we have a demand of 51 patients needing admission, we will need to discharge 51 patients to prevent long waits in ED from occurring. So we can start to introduce this as a metric and a target on our existing dashboards. And we've also used this to kind of support our narrative around annual planning. So all of the outputs from the project are available on GitHub, and a deployed version of the model is also available on Streamlit Community Cloud. So I can post those in the chat. And thank you very much for listening. And thanks very much to Sammy and Dan for providing the support for this project. Thanks to everyone else who's been involved with it as well.